Hey guys, feel free to ask me any questions. I'm here early just in case y'all had questions, but you're not required to ask me anything, but I am here.
Hey, I had a quick question regarding the modules on Canvas.
Mhm.
So I'm confused. Are we supposed to be registered into two Canvas like pages, like one for the lecture and one for lab, or is it just one?
No, you are in NO2B, right? You're in this class, not the other 241 class.
It's the 241 class that I'm in.
Okay, but I've got two of them going, so I'm trying to make sure you're in the N02B one, not in
One minute. Let me just make sure.
no problem.
Um, I'm in the O01B.
Okay, so there might be two different pages for your lab since you're in O01B. That class has me as the lecture instructor, but it has someone else as the lab instructor.
Oh, okay.
So when you sign up for that class, they normally make you take a different 241 lab that might be L02B or L03B or something like that. But what I do with my N02B, which is the class you're in right now, and you're welcome to attend. That's why I made it this way so you could attend.
Mhm.
But what I do in this class is, in fact, I just changed it today. I'm using one Canvas course for both the lab and the lecture. And today I started separating the modules. So I have a week one module for lecture, and then I have a week one module for lab. And that's the way it's going to be in this N02B class. I'm making that statement obviously not for you because you're not in
Yeah.
the lab, but just making sure that's clear. So yeah, your instructor, you might have Mr. Johnson or you might have Miss Raskovic. Do you know which one yet?
No, it doesn't really say which professor that I have under, so I'm just confused. Because right now I can see that I'm in the L01B lab, but it's not published for me on Canvas. So I was just confused on where to go to get that published so I can get started on the labs.
Okay, well, let me double check something on that because there's some probability that that I might be misunderstanding what's set up here. So let me double check in my SIS. My understanding was that I'm teaching a or excuse me, a asynchronous class. That's the 241010B or 001B, excuse me.
Mhm.
And okay, no, it's my fault. Yep. I'm looking at it now. It looks like the O01B class has the lab section L01B. So you are actually in the right place, but I think I've been putting the lab in the wrong section. So what I'm going to do is take and copy the stuff that I put in the L01B. I'm going to put that in the O01B class. You've only had two labs, and both of them are well. I've set up the lab Tuesday, and that was really a pretty simple, straightforward lab. And then I set up a lab today, and that's also a straightforward lab. I misunderstood the way this was assigned, but now I'm looking at it, I see that your class, the O01B, is supposed to have the lab L01B. So all of your stuff will be in your lab, and I'm thankful for you asking it because that will now make me make it correct. So I'll fix that right after class, and I'm going to give you a huge extension for the first two labs. It shouldn't be a problem because the first two labs are really simple.
Okay, that sounds amazing. All right.
Sorry about that, Isham. Thanks for
Yeah.
catching me on that. I've been
Yeah.
going back and forth between three different SIS pages, so I hadn't looked close enough to be able to tell. And all this time, I've been thinking that was L01 that's getting that. So thanks for
Okay.
calling
Yeah, no problem.
me. Anybody else have any questions? Oh, guys, that's terrible news that I just found out, though. But anyways, we'll get her fixed. Your instructor might be a goober, or completely is a goober. We still got about 4 or 5 minutes before the class is supposed to start. But y'all, like I said, you're welcome to ask me questions. I might even right now while you're in here, I think I'm going to go ahead and try to move some of that lab stuff to the appropriate place since I'm such a goober. Ah, God, that makes me mad. Here it is. Hmm. Oh, got some more people coming in. That's good. A lot more people coming in. They should be ready to roll pretty soon. That's it. All right, it's time to get started, everybody. Hello, thanks for coming. I see I've got about 11 of you in here. That's pretty good. I want to let you know that one of your students just saved my neck. I wasn't paying a close enough attention to my many windows of SIS that I have, and I have been putting your lab stuff in the wrong Canvas course, but I just corrected it. So if you look in your Canvas course right now, you'll see there's a week one module. It now has the correct date. I thought I'd already corrected that, but it was showing January, so it wasn't correct. But if you look, there will be a week one module and it'll say, May 20th to May 26th, and it'll say something about the lab being in the next module. And then if you look immediately below that, you'll see week one lab module, and that'll have all the stuff for this week's lab, including a link to a video that gives you sort of an introduction. It's a generic introduction, but it was for last semester. So if I happen to mention any dates or anything like that, that would be last semester dates and not relevant. Uh, but other than that, the whole introduction to the lab is perfectly straightforward. There's also an addendum in there. That addendum is what you'll have to use the whole semester to make your lab, which would normally be a face-to-face lab, into a lab that you can conduct at home without a lab partner. So you need that addendum. Normally, what happens is you read the lab document first and then you read the lab addendum. So you'll see the lab documents in there as well as the addendum. And then there's an assignment where you turn in the lab and you'll see that'll have a date listed on it. So that's when that's due. Right now, I have the lab that I posted on Tuesday. That is supposed to be due this coming Tuesday, in other words, right after the weekend. And the lab that I posted today was supposed to be due a week from today. And I'll leave that right now. But if you find you have any problems getting those labs done, let me know. I'm going to give you at least until Sunday of next weekend, just because I put the lab in the wrong place. So if y'all need more time, that'll be fine. But I really think y'all won't have any difficulty getting it done on time, because the two labs that we did this week, which is Intro to Lab and Intro to Excel, they should be really, really easy for you guys. So I doubt you'll have any problems. What I do recommend also is you'll see there's comments, like there's something called Intro to Lab Comments Master. And I highly recommend you read those comments whenever they're available for a lab before you turn your lab in, because what they are is they're literally statements that I've made to students about mistakes they made in turning in the lab. So by you doing that and looking at that before you turn in your lab, you might be prevented from making another mistake on your lab report before you turn it in. So hopefully that'll help you. It might be a little too complicated for you to look at some of the statements that I make and understand it, but I think it should be pretty good, especially once you've read your lab already. So do check that out. Like I said, there's two labs up now. One's intro to lab, and uh, with that one, it even comes, the addendum comes with a piece of paper with a picture of a meter stick on it, and you're literally supposed to use the meter stick that you print out as a picture. You're supposed to use that like a meter stick to measure things. That works just fine. It really does. So you can use that, and you're going to measure instead of very specific cylinders and stuff that we had in our labs. You're going to just go find soup cans and bottles and stuff like that from your own house and measure those so you can get an idea of how the circumference relates to the diameter, which is part of the lab. It's got other things also. For instance, they give you the actual measurements of 100 grams weights that we use so that you can see that even though those weights get all beat up and look crappy, still very precise. So anyways, just check that out. And I apologize for setting that up. I'm pretty confident I even did the syllabuses uh, inconsistently, in other words, incorrectly. So I have to go back and redo all those at least over the weekend. So I have that done by Monday. Everything about the syllabus is right, except like I said, I was under the impression that the O01B section was not linked to the L01B lab. That the L01B lab was linked to the N02B class, which is what your class is. So I apologize for that. If you're in N02B, it's my understanding that you're actually attending a lab done by Mr. Raskovic or Miss Rastovic or Mr. Johnson or something like Dr. Johnson or something like that. So just let me know if you're different from that scenario. And like I said, we can work out a scenario to help you with any difficulties you're having. But that should do that. I see I've got some mentions here. I'm reading those real quick. Thank you, Darius. Yes, Adrian asked if students can join in if they're from the asynchronous class. Absolutely. That's why I had to make this in the Zoom. That's not for our class. I had to make it in the general Zoom app that I have for instructors. That way, both my 241 001B and my 241 N02B can attend it. So yes, you're absolutely invited and encouraged to attend. Michael Jones posted something. Gotcha. He's just let me know that he is taking it. I thought that was the case. I thought Mr. Johnson was the one, Dr. Johnson, I should say, is the one that had the lab that goes with the N02B. So I apologize. You will see some random lab stuff in your N02B Canvas course. You're not supposed to do anything related to lab from me. Some of the stuff I'll leave there for you, like my document on uh, significant figure rules, as well as when significant figures fail, that sort of stuff. So I'll leave those there because that can just be helpful to anybody. But you will not be turning any labs into me if you're in N02B, unless you happen to have worked out some deal with me about trying to take one of my other lab sections. Okay. Anybody have any questions before we get started? This is the beginning of every class is your chance to also ask any questions you might have on not only past stuff that we talked about on the syllabus and how the course works, but also about your specific homework. So if you started any chapter one homework or even chapter two homework, you can ask questions like that too. So does anyone have any questions? I'm reading the comments as they come up. Hmm, got that, got that. Okay. So if I jump into class and forget to offer that time at the beginning to answer questions, by all means, if you have a question, stop me and ask me. And if you feel a little shy about it, don't, because there's probably three or four other students that are having the exact same problem. They really want someone to step in, so you can be the hero. get that done. But yeah, just make sure you stop me because I get really excited when it's time to start class, and I'll just come in and start talking and completely forget to offer y'all a question and answer session. So let's go ahead and get started. I will let you know a little bit later. I'll probably at least wait till after our break before I ask you to chat me your first and last name for your attendance. Uh, so that's going to be, again, how we do that every day. And I want to remind everybody, like I did in the last video, which this part didn't actually necessarily make it on the video because I inadvertently did not record the first hour. But I just want to remind you guys that this video that I make will go on to YouTube, onto my YouTube channel. And in principle, anybody in the world can just click on my video and then they'll see this video and they have the possibility of seeing your specific name, your username more specifically. And if you're sharing your image with me from your video feed, then it'll show that as well. If you have any kind of conditions that make you want to not be seen like that on the internet, you need to, one, make sure you change your username within Zoom so that it doesn't show your name. You can just do like a first initial and the whole last name if you want, and that way I can still tell who it is. But the main thing is you got to also let me know that so I can try to make sure I don't put you in there. Uh, I don't really have a skill set yet of how to cut out individual parts of a video. I probably could figure it out, but the main thing is I just don't want to endanger anybody or cause problems for students. So by all means, just remember all of this is going to be posted online, and unless you explicitly tell me I can't, uh, then you're going to be on there. And I, like I said, I just don't want to cause any problems for anybody. So still no questions? All right. Well, we've got a lot larger fraction of the class now. We've had maybe five more people log in since I started. When we last talked, we were in chapter one. I had covered some stuff from chapter one. Specifically, if you look at chapter one, the sections of chapter one are how science works, models, theories, and laws, measurement and uncertainty, significant figures, unit standards, and the SI system. I had sort of covered those first three sections, how science works, even though I gave you a description of it based on the way I try to tell and teach students how science works. The same thing with section 1, 2 on models, theories, and laws. What I want you to realize is that the word theory is a strong word. It should never be used with a diminutive adjective like it's just a theory. Okay. In the modern definition of the word theory that we use in science, and we should be very consistent about using, though we often make mistakes, is that a theory is a very, very strong thing. It's basically a hypothesis, and it might even be a whole paradigm based on some very specific hypotheses that have went through numerous experimental checks and never once been found to be an error. Okay. Once that happens on the order of hundreds of thousands or millions of times, that hypothesis and paradigm slowly converts itself to a theory. And that's impressive, but it's also still not the law. And in fact, the word law is also just another word for theory, but historically it often has the word law in it. But it doesn't mean anything any more serious than the theory. So both theory and law are very serious, strong terms that means that a great deal of experimental analysis has been done, and it's never been found to be an error. So when we say things like the special theory of relativity, the general theory of relativity, quantum mechanics theory, or the theory of evolution, all of those are very strong words, and we literally have zero evidence of them being incorrect. Zero evidence of them being incorrect. But it still just takes exactly one experiment. If you do one experiment properly, and you don't have to have a degree, you don't have to have a PhD, you don't have to be brilliant. You just have to be a person that did a replicable and repeatable experiment. And if it shows that some grandiose law is wrong, then it will be overturned. The law will be overturned, and it doesn't matter at all. So even though it has this classification of law or theory, which is a very strong phrase, uh, science is very much about getting rid of dogmatism. So all we want is only things that can be verified experimentally. and can be nullified experimentally. And that's sort of the quick version of what you missed on that video. If you actually, most of you were probably here when I did it, but it just didn't come out in the recording. So I just wanted to recap that. Section 1.3 was where we started into measurement, uncertainty, and significant figures. And I covered a little bit of that last time. Remember, we talked about basically, if you're trying to make a measurement, let's say you're trying to measure the length of this pin, what you want to do is take let's say a meter stick or a vernier caliper, both of which are marked in increments of 10 spaces between 1 centimeter and 2 centimeters. That means they're marked to the nearest millimeter because a tenth of a centimeter is a millimeter. And because of that, you absolutely should never get the first decimal place wrong if you report a measurement in centimeters. Okay. So using a vernier caliper or using a meter stick, the measurement up to the first decimal place in centimeters can never be wrong unless you just read it goofily, because it's literally marked on here and there's no ifs, ands, or buts about it. The next digit, though, should be included, except under the most strange circumstances. The next digit should be included because that is how many digits you can get when something's marked to the nearest millimeter. Then you can get two decimal places in the nearest centimeter. Okay. That does not mean you just put a zero on the end of the one decimal place number because that's sort of cheating. Okay. It really takes a little bit of work to make sure you got a zero in that spot. So don't just after the fact go back and add zeros when you get ready to turn in your lab. Just admit that you made a mistake, write it there, explain it to me, and you'll lose less points when you turn in a lab that way. So keep that in mind whenever you're making measurements with either a vernier caliper or a meter stick. You should report two decimal places when you're using units of centimeters. Okay, no less than two decimal places. The uncertainty, if everything's going perfectly well with the meter stick, the uncertainty is plus or minus 0.02. Maybe in a really good scenario, you might even argue that's 0.01, but I really think the best estimate is 0.02. If you're doing yet less than ideal conditions, like reading across some distance and trying to eye whether it lines up or something, then you're going to have to start using your brain and figuring out whether it's better to say that error is 0.02, 0.03, 0.04, or maybe even 0.05. Okay. The main thing is you always have to have that instrumental error for every device you use from the very beginning. Write down what you think the instrumental error as soon as you start making those measurements. And then what you're going to do if you want to, for instance, determine, like I said, the length of this pin, you're going to measure it and you'll write down the number. Obviously, if you're using a vernier caliper or a meter stick, then you're going to measure that to a certain number of centimeters read to two decimal places. And then you might find that that number doesn't necessarily match the same number that someone else got. So what you do then is you say, well, maybe I made some kind of systematic or random error. Well, systematic error is almost impossible to get rid of, at least from an experimental standpoint. Uh, after the fact or whatever, you can sort of, if you figure out exactly what you did wrong, you can mathematically make corrections, but that's not really the way lab's supposed to be done. But if you make a random error, you can do multiple trials. And since the error is random, there's a high probability that you'll make just as many random errors that make the measurement too small as you do random errors that make the measurement too big. So by taking multiple trials, you can eliminate a lot of the random errors. So that's why when we go to measure, for instance, this pin, we might actually take 5, 10, 15, 20 measurements of it. And then the question is, what is the best estimate? Well, it's the average. And again, just to make sure you completely understand, the best one would be a weighted average, meaning you made a measurement and that measurement not only had a measurement of what you thought the length of the pin was, but also had an estimate of what the uncertainty of that measurement was. So you'd have both of those pieces of information from that first trial. Then you have both of those pieces of information for the second trial, the third trial, the fifth trial, for all the trials. Then when you have that, what you want to do is a weighted average. We're never going to do that in the class for any particular lab experiments. But I want you to know that obviously a weighted average is superior to a regular average. But generally, the average is just if you did 5 trials, you take the 5 numbers, add them up, and divide by 5. So that's your best estimate of the measurement that you made. And then, as I pointed out, the best thing to put after the plus or minus, because like I said, in a experimental or lab setting, if you're reporting a result, you should report the result like L is equal to 3.54 centimeters plus or minus zero point zero 0.02 centimeters, something like that. Okay. Well, that number that comes before the plus or minus, as I said, is the best case scenario would be a weighted average, but at least it'd be an average. And then the number that comes after the plus or minus is what we call the standard error, which is also called the standard deviation of the mean. It's explained a little bit about how to calculate that, but you'll have a lab later to show you. So that's pretty much all we really covered. And I'm going to leave the rest of that significant digit stuff and error and uncertainty stuff. I'm going to leave that up to you reading your book, and two, up to our propagation of error lab, which will come later, and three, up to the documents that I put in your Canvas page where I teach you the significant digit rules. There's a document literally called significant digit rules, and there's some links to uncertainty and stuff like that that you can check out. So we're going to leave that be. And now we can go on to the rest of chapter 1, which, as I said, we had already started. We'd already done measurement, uncertainty, and significant figures, and we were into unit standards and the SI system. I will remind you that I did tell you, what the modern definition of a meter is, what the modern definition of a second is. And it's important to understand that you have something like that, and that you have the understanding that we're trying to move those to concepts that anybody could actually repeat, as opposed to having some particular sample that we have to, take from one place to another. And if, some kind of horrible accident happened with that particular sample, we'd be kind of blown out of the water. We're trying to get away from those types of base figures. So, for instance, right now we have a platinum iridium cylinder in France that basically occasionally we pull it out, and it represents the standard kilogram. And in order for us to test that against other things and to make sure everything's calibrated in all the labs, not only just in France, but also all over the world, in some sense, we have to compare that particular 1 kilogram mass to the 1 kilogram mass that we might have locally at our particular lab. And that's what we're trying to get out of. We don't want a physical object that you have to move around. We want a concept or a procedure that we can explain to the world, and then anybody can repeat exactly that same procedure and at their location, even if it's in a distant planet around a star that's not our sun, they could still find out exactly what we mean when we say 1 kilogram or 1 meter or 1 second. So let me go ahead and share my screen with you. We're going to get cracking on the rest of chapter 1. So I'm sharing my iPad screen with you now. It should pop up any second. And I mentioned that we are using the SI system. And just to rehash that, I'm going to list the parts of the SI, the prefixes of the SI system, with using my own internal mnemonic in my head. So I advise you all to find your own mnemonic, but I'm going to start like this. Those dots are important, by the way. So T, G, dot dot. So it's T dot dot G dot dot M dot dot. Notice that's a capital M. And then K. Notice that's a lowercase k. And then, okay, so each of these are prefixes. The T is tera, the G is giga, the M is mega, the K is kilo, the H is hecto, the D is deca, D-E-K-A. And then we have the base unit right there in the middle. So we call that base. And then we have a tenth of the base, which is a deci, and then 100th of the base, which is a centi, and then a thousandth of the base, which is a milli. Notice that's a lowercase m. And then we're going to have dot, dot. The next one is a Greek mu for micro, dot, dot. The next one is a N for nano, dot, dot. The next one is a P for pico. And it actually goes further to the left and further to the right. But these are probably what I would say is the bare minimum that you should commit to memory just to be a functional human in the classroom. Okay. That being said, when you start taking your practice test, you'll see that the inside cover photos that I have down at the bottom of the practice test has these prefixes with their power of 10 equivalent listed. So you technically don't even have to memorize that. But in this order, you should be able to see exactly what that is. So for instance, deca means if you take the base, and the base, by the way, could be, for instance, a meter. That would be the unit of length. Or it could be a gram. Technically, when you use an equation that is designed for the SI, like all the equations we'll be doing this semester, if it has mass in it, you're supposed to put the mass in kilograms. So in that sense, that's the base unit. But in reality, the base unit is the unit without a prefix on it. So this one's grams, okay? And then seconds, S. Now, as time goes by, you'll learn other things. Some of them are just made of these, like, for instance, the unit of force is the Newton, and the Newton is actually a kilogram meter divided by a second squared. So we actually got a unit of force from the unit of length, the unit of mass, and the unit of time. So sometimes they're like that. Sometimes they're brand new units, like the mole. And that's a measurement of the quantity of material. Another one's a lumen, so on and so forth. But the main thing is whatever that base is, that's what you'd put right here in this middle. So if you have a measurement in meters, then that measurement would be represented by this underline. If you had it in grams, it'd be represented by this underline. If you had it in seconds or moles or Kelvin or whatever, again, all that would be in this base part. So I'm going to go ahead and write this. All right, now this deca to the left is when you go to the left of the base, you're trying to find units that are bigger than just the base. The base would be the meter or the gram or something like that. And in fact, we're using a rational system. So we're not going to be using weird things like 1 quart is 2 pints, but 1 gallon is 4 quarts. But 1 cup is 8 ounces and stuff like that. They're historical numbers with no real rhyme or reason. The rational system of units, that is the SI, is basically based on powers of 10 being the more natural course. So if you want to increase the base unit by a factor of 10, then you use deca, and that means times 10 to the 1. Hecto means times 10 to the 2, and kilo means times 10 to the third power, or 1,000. Notice the dot would be where 10 to the fourth is, and then the next dot would be 10 to the fifth. We don't do prefixes for those. Once we get outside of kilograms and milligrams, we actually do nothing but increases by a factor of 1,000. So this one's going to be times 10 to the 6. So mega is like a million. Giga is going to be times 10 to the ninth, so that's like a billion. And tera is going to be 10 to the 12th, so that's like a trillion, at least in America. If we look at going to the right, then the unit's going to be a smaller unit than the base unit. So if you wanted to measure something smaller than a meter, say, you might want to consider a decimeter, which would be times 10 to the negative 1, or a centimeter, which would be times 10 to the negative 2, or a millimeter, which would be 10 to the negative 3. And then, of course, there's nothing for 10 to the negative 4. There's nothing for 10 to the negative 5. But there is something for 10 to the negative 6, which is micro, 10 to the negative 9, which is, or excuse me, 10 to the negative 9, which is nano, and 10 to the negative 12, which is pico. The femto is the next one, so on and so forth. But again, you shouldn't need that. Just to let you know what they are, I'm going to say this is tera. Actually, I think that's a single R. I'll just say them, but you can look in your book or on the documents that I have saved in helpful links and documents and see that T is for tera, G is for giga, or if you saw the movie Back to the Future, you'd say it's giga. I pronounce it with a hard G, giga, but like I said, in Back to the Future, they pronounce it with a giga, like it was a J as opposed to a G. M is mega. That's capital M is mega, K is kilo, H is hecto, DA is deca, DEKA. Lowercase d is deci, DECI. Lowercase c is centi, like a cent, like a 1 penny. And lowercase m is milli, MILLI. Uh, the the Greek symbol mu is for micro, and then the N is for nano, and the P is for pico. So that should help you. Now, in addition to understanding these base units, we also have a problem in that we're in America, and us, and I think like Myanmar or Liberia or some very, 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 very small country, other than the United States, obviously, but some very, very small country and the US are the only two countries in all of planet Earth that actually uses the British system. Okay. So because of that, we're going to have to occasionally convert things back and forth between the British system and the System International, or between the CGS and the MKS and all that stuff. So there's certain things you need to know. Uh, the things that I normally know off the top of my head are some facts like this, like 1 mile is equal to 5,280 feet, which is also written 5,280 with a single hash mark. 1 foot is equal to 12 inches, which can also be written by as 12 with a double hash mark. So inches is a double hash mark, feet is a single hash mark. Uh, the one factor that converts between the British system and the metric system happens to be exact is 2.54 centimeters is exactly equal to 1 inch. So that means that's 2.54 followed by an infinite number of zeros for the remaining decimal places. So that's exactly correct. That's some of the stuff you need to know. You also should know that, for instance, well, let's see. That got me feet, inches. You should also know that 1 hour is equal to 60 minutes, and that 1 minute is equal to 60 seconds, and that 1 hour is equal to 60 times 60 seconds, which equals 3,600 seconds. So those things come in handy as well. And these statements where I say something in one unit equals something else in a different unit, these are called equivalent statements. And they're going to come in handy because I have to teach you how to convert back and forth between units. And the way I'm going to do that is I'm going to convince you that there's a certain types of units in the world uh, that don't work the easy way that I'm getting ready to teach you. Examples of those are Celsius, Kelvin, Fahrenheit, Rankine, and decibels. Those are ones you've probably heard of. You might not have heard of Rankine before, but Rankine is to Fahrenheit exactly the way Kelvin is to Celsius. So hopefully that'll help you. But in order to convert back and forth between units, if they're those types of units, there's very specific formulae and processes you have to go to convert back and forth between decibels and sound intensity, are decibels and voltage, which you might not recognize because you've not had the experience yet. But if you ever happen to be around when a Dish Network or DirecTV or Mediacom or cable company shows up at your house, you'll notice they use a device that measures how strong the signal is coming in the wires that go to your television, and they measure that in decibels. Okay, we're used to decibels being an intensity of sound, and the reason why they use the same name is because the formula is the same. It's basically 10 times the log of some ratio. And the fact that it's multiplied by 10 is what makes it a deci, because it's a tenth of a bell. A decibel means a tenth of a bell. But it's comparing either to the original signal that came out or some standard version, so say some number of watts per square meter that land on a little bit of a human ear, for instance. That would be one of the ratios you use in doing decibels for sound. Decibel with a B for sound. So as long as we're ignoring those weird things like, converting back and forth between Kelvin and Celsius and between Celsius and Fahrenheit and between Fahrenheit and Rankine and all that, as well as between decibels and intensity and decibels and signal. If you're not doing those, then there's something called the factor label method that we use. So I'll write that here. The factor label method of unit conversion. Hopefully, you were good students and managed to get through chemistry in high school, in which case you already know about the factor label method. But you might have been such an awesome student that you weren't allowed to take such advanced classes as algebra or chemistry or physics, which is what my life was like. So I didn't get that. I did actually get to take chemistry, I should say, but I did fail it. So that's how awesome I was. Uh, anyways, that's part of the ongoing story about Mr. Younger and his sordid life. But anyways, the factor label method is based on this. You know that there's a special number in nature that you can multiply by any number and it doesn't affect a number. Can anybody tell me what number you can multiply by a number and have it not mess up the number? Like if I had the number 4, what can I multiply by 4 and not screw it up and make it different from 4? I really thought you were thinking on that one, Andrea. I could see it in your face. I was like, ah, she's going to answer this time.
Is it one?
It is 1, absolutely. Yeah.
Okay.
So yes, and that's the key point. So the only number that you can really multiply another number by and not change its value is 1. The key to the factor label method is realizing all the different versions of 1. So here's your versions of 1. We have the number 1. We have the number 1 over 1. We have the number 2 over 2. We have the number pi over pi. All of those are fine. Okay. Now let's get a little bit more abstract. We also have the idea that 1 foot is equal to 12 inches. That's also 1, because it's not only something that when you divide the top by the bottom, you get 1. It's also whenever the top is equal to the bottom, then the number is 1 as well. That being said, obviously 0 over 0 is a whole different beast, so we can't do anything with that. My daughter's calling me. All right, I got that fixed. Now, additionally, that's not the only way you could write that same one. You could also write 1 foot on the bottom and 12 inches on the top. And of course, you could also use the hash marks like I did above, and that would work as well. You could also say that 1 inch is equal to 2.54 centimeters, stuff like that. So all of those are different values of 1 that can help us convert units. So that is the key to converting units is just finding the appropriate value of one to multiply by the number we have to get the units that we want. So for instance, you might wonder, uh, a football field is supposed to be 100 yards from goal line to goal line. So what would that be, let's say in meters? So I'm going to say the problem is convert 100 yards to, let's be crazy, let's say to centimeters. Okay. So what I'm going to do is I'm going to write 100 and then I'm going to put YD as the abbreviation for yard. Now I'm getting ready to multiply by a fraction. So what I've learned is that students are still sometimes a little shaky with their fraction work. So I try to give you hints to make sure you don't make little careless mistakes. So I apologize if you know better than the things I'm telling you, but I'm going to tell you anyways, just to make sure everybody's on the same page. So the first thing I do is I go ahead and write the number I'm trying to convert. If it's not already in a fraction, I make it by into a fraction by putting it over one. Okay. Now, the next thing I want to do is I want to look for some fact that allows me to make a equivalent statement that I can make into the number one. Like, for instance, I happen to know that 1 yard is 3 feet. So using the equivalent statement, 1 yard equals 3 feet, I can do like this and say, okay, well, I'm going to multiply this by a fraction. And in order for me to get rid of the yard, it's obvious that the yards has to be in the bottom. So I'll put the yard down there and I'll put the foot up top. And what I know is that 3 feet is equal to 1 yard. And you can see that the yard is going to cancel out with this yard. Notice I went from top right to bottom left in slashing through that yard. You can use that as a bookkeeping technique to make sure you check that you canceled out the right thing with the right thing by changing up the different thing you use for different units. So right now I've just converted 100 yards to the certain number of feet, which you can probably already tell it's going to be 300, but I'm not getting closer to meters yet. So what I'm going to do is get to inches and then I'm going to convert from inches to centimeters, and that's the way I'm going to work it. So now I need another equivalent statement between feet and inches. Can anybody think of an equivalent statement between feet and inches? You can blurt it out. You don't have to raise your hand or anything.
12 inches over 1 foot.
Exactly. Now, 12 inches equals 1 foot is what I would call the equivalent statement. And then there's two ways you could put it. You could put 12 inches on top and 1 foot on the bottom, or you could put 1 foot on top and 12 inches on the bottom, but you rightly notice exactly the right way. So you're going to say 1 foot is on the bottom and you're going to say 12 inches is on the top. Now, notice how I mark out this foot. I'm going to go from top left to bottom right this time. See how I used a different slash mark for the two different unit crossings out? So now I've gotten, instead of having 300 feet, now I have 3,600 inches is the length of a football field. And I'll explain how you do the math on this later, but so far what I'm giving you is ways to figure out how to do the math based on what I said. Now I'm trying to jump from the British system into the metric system. And I told you there's one specific conversion that's really helpful for us, and that is this one right here. Oops. This one right here. I like it because it's an exact statement. 1 inch is exactly 2.54000000 for infinity centimeters. So should I put the 2.54 on the top or bottom? Should I put the inches on the top or bottom? Anyone? Well, in case you hadn't noticed, we are trying to get rid of the inch. So the inch will definitely be on the bottom. And if you look at our equivalent statement that I circled a second ago, you'd see that the inch comes with the number one. and that the centimeter, which is obviously going to have to be on top now, comes with the number 2.54. So that's actually what we've got here. Now I've got to cross out the inch. So what I'm going to do this time is actually do a full X. So you might think, well, he's ran out of methods now, and that's okay. I'm going to show you some other ones that we can use. But now we're up to centimeters, and in fact, that's one of the answers that I asked for. I was going to say to meters, but we can do to centimeters and to meters. We already have the answer in centimeters. So what I'm going to do is I'm going to tell you how you do this math. So when you're doing multiple steps like I did in this one, notice I had 3 conversion factors. Uh, what's the easiest way to deal with this is just multiply all the numerators to get a new numerator. So I'm going to take 100 and I'm going to multiply it by 3, and then I'm going to multiply that by 12, and then I'm going to multiply that by 2.54. And that gives me 9,144. And that's the whole answer. And notice the only unit I have left is in the numerator, and it's centimeters, so I'll put that there. Now what I do is I multiply all the denominators. In this case, it's really trivial because all the denominators were 1, but still, that's what I'm going to do. So I'm going to do 1 times 1 times 1 times 1, and that's just going to give me 1. And in fact, we're going to say that the answer is 9,144 centimeters. That is what a football field's length is in centimeters. I'll say and in meters now. So I added to the question and I added a second part. The second part is now let's convert it to meters. So what I'm going to do now is show you how I can use the mnemonic at the top, the letters for the SI prefixes. I'm going to show you how I can use them to make equivalent statements. What I know, for instance, is I can look at the tera, say the T, and I know that's bigger than the base unit. And if we assume we're in meters, we could say that 1 terameter is actually equal to 10 to the 12th meters. And that's an equivalent statement. It's 100% right. But notice I went from the object on the left, I took the number that's above it that represents the power it represents and put that with the unit that's on the right. If you do it that way, it'll always work. Uh, you can easily get into a conundrum, though, if you try to do it a different way. So now let me look at, for instance, conversion fact or a equivalent statement between meters and, let's say, micrometers. So for instance, 1 meter, if you look at that one, you'd say, okay, well, there's 1 meter here. And if I go to the right, then I could actually look for the equivalent in micrometers, for instance. And what I would find is that in this case, we'd want to do the same thing. We'd actually want the thing that's not the base unit. We'd want the number that's from that to go with the base unit, just like we did before. So if I do that now, you can say, okay, instead of writing 1 meter, I'm going to write 10 to the negative 6 meters, which corresponds to this space right here. And I'm relating it to this space right there. So I'm going to say that is equal to 1 micrometer. So that's how you can make an equivalent statement. There is a way in principle you could go straight from tera to micro, but I'd tell you it's much more complicated to work through that, especially in the stress of a test. So I'd totally go to the base unit and then to the other side of the base unit. So some more examples: 1 gigagram is equal to 10 to the 9th grams, or let's say 10 to the negative 12th seconds is equal to 1 picosecond. So that's how you can make up these equivalent statements from the little letters that I have marked up top. Now I'm going to use that to convert my centimeters to meters. Okay. So for instance, I'm going to take my centimeters and I'm going to take my meters, and I see my centimeter has a 10 to the negative 2 on it. So I'm going to write 10 to the negative 2, and now I'm going to write the base unit, meter, and now I'm going to write equals 1, only this time I'm going to use the prefix, which would be centimeter. So 10 to the negative 2 meters is equal to 1 centimeter. With that being said, now I can go ahead and do part B. And what we have is 9,144 centimeters. And like I told you, when you're converting units, you want to go ahead and make it into a fraction. Now I'm going to use my red to show the work I'm doing. This time I'm looking for an equivalent statement between centimeters and meters. Do I want the centimeter on the bottom of this red fraction, or do I want the centimeter on the top of this red fraction? Anyone?
On the bottom.
Very good. And that's because it cancels out, just like, an X and an X at the top and bottom, or a 2 and a 2 when you're converting when you're reducing a fraction. So we know that 1 centimeter is equal to 10 to the negative 2 meters. And what we can see is at this point, the centimeter cancels out with the centimeter, and I just get 1 times 1 on the bottom. So 10 to the negative 2, if you want to actually use your calculator to do that, I'm going to tell you 10 to the negative 2. Hold on, let me rewrite this a little better. 10 to the negative 2 is equal to, on your calculator, you want to type 1, and then your calculator is going to have a button like times 10 to the x, or it's going to have a button that is exp, or it's going to have some other kind of button like that. And it'd be negative sign and 2. I should say that is not the minus symbol, that is the plus or minus negative sign. So I'll write it this way. Okay, so just be careful. Students will often type in 1 times 10 to the negative 2, but they'll just write it like that, and they often come up with a factor of 10 off from the actual answer. So I wanted to make sure you guys knew what I was doing there. What we do here is we're going to say this is 91 point, oops, I should write in black like I was doing before. I did that other color on purpose, but this would be 91.44 meters. And that's how big a football field is in meters. It's 91.44 meters from goal line to goal line. Anybody have any questions on that one? All right, so again, remember there's some types of units that we haven't addressed here. We haven't addressed converting back and forth between Celsius and Fahrenheit and Kelvin and Rankine. We also haven't addressed decibels, but virtually everything else you can do this way. Not only that, it's super powerful. You'd be surprised how many times just unit conversions, all you need to understand a lot about something. This is literally how I became a certified pool operator. Discovered that basically all their calculations were unit conversion calculations, and I was able to quickly figure that out, and they promoted me rather quickly to run the pools when I was in high school. So that's a valuable thing to have just as a human being, not as an engineer, not as a scientist, not as a physicist or whatever. Just being a human, knowing how to convert units is super, super helpful. So let me move on to something a little more complicated. Let's move on to miles per hour. So my mother used to say, I was a bit hyper child. So my mother used to say, your mouth is running a mile a minute. So let's try to convert a mile a minute to miles per hour. So what is 1 mile per minute? miles per hour. Okay. So what I'm going to say is 1 mile divided by, remember mathematically, when you hear the word per, that's sort of code word for divide by. So when you say I get 12 miles per gallon, that should tell you, oh, you're going to take the miles and divide it by the number of gallons. And that's exactly what the per means. So when someone says 12 miles per minute, I'm going to write, or excuse me, 1 mile per minute, I'm going to write 1 mile over 1 minute like this. Now I know I'm going to have to convert this. The miles per hour tells me that the mile up top is just fine. I can leave that be. I don't have to make any conversion there. But what I do want to do is change that denominator from minutes to hours. So first off, anybody recall how many minutes are in an hour? Right, 60, right? So should we put the minute on the top or should we put the minute on the bottom when we go to make this red fraction that we're going to use to convert? Because the minute that we're trying to get rid of in the bottom is in the bottom, we're going to put the minute on top so that it'll cancel it out. And what we know is that 60 minutes is equal to 1 hour. So we can see now that the minute's going to cancel out with the minute, and the math works out to be 60 miles divided by 1 hour, which equals 60 mph. So if your mother ever told you your mouth was running a mile a minute, now you know that that just meant 60 miles per hour. Yay. All right. Now I'm going to notice the difference with that one. The difference with that one is we were only addressing the conversion of the thing in the denominator. So that's a little different than what we did before. Before we were only dealing with things in the numerator, but you can actually convert things in the denominator, and you can even convert things in both the numerator and the denominator. So let's look for another example. This time I'm going to say, what is 60 miles per hour in A, kilometers per hour, and B, meters per second, because meters per second is what we're going to be using normally in the SI system. Okay. So let's start off with 60, and I'm mostly going to just do this one for you because it involves a lot of steps and takes a lot of time. And rather than, asking you each time and then waiting a long time, I wanted to go ahead and get through it. So let's go ahead and get started. We're going to say this is 60 miles per hour. So I'm going to write that as 60 miles on top and 1 hour on the bottom. Now I'm going to use red to draw my equivalent values of 1, basically. So to make my fractions. Now, what I'm going to do is I'm trying to go first off to kilometers per hour. So right now I've got the per hour, and that works great for the kilometers per hour. So for part A, we'll just run with this. Oops, that should have been in red, in black. So for part A, we'll just run with this. But I need to convert from miles to kilometers. So what I know is 1 mile is equal to 5,280 feet. So I'm going to write 1 mile on the bottom, and I'm going to write 5,280. This time I'm going to put a single hash mark because it takes less time than writing an actual FT. So I've got that. Notice that mile cancels out with this mile and leaves me with just feet in the numerator. Now I've got feet per hour, but I'm trying to get to kilometers per hour. So I know a way that I can get to the metric system by going through centimeters to inches. So I'm going to get to inches. Now I'm in feet. So now I know that 1 foot is also equal to 12 inches. So this time I'll use a different color mark, but basically I'm going to put an X there and an X there to mark out the feet. And now I can see I've got inches per hour. Now I'm going to go from inches to centimeters, and I know that 1 inch, which I can mark again with the double hash mark, 1 inch is equal to 2.54 centimeters exactly. So basically, if we use 3 sig figs coming in, the answer can come out in 3 sig figs. If we use 50 sig figs going in, the answer will come out in 50 sig figs. That's because all these conversion factors I'm using are exactly correct. So now we can cancel out the inches, and you might think we've ran out of stuff. So I'm going to do a curved from the top left to the bottom right. That'll mark out the inches. I still haven't used from the top left to the bottom right as a straight line, but that's because it would have been confusing with these hash marks, so I chose not to. But now I've gotten it to centimeters per hour. Now all I need to do is convert from centimeters to meters and then from meters to kilometers. Again, if I look back at this, I can see that centimeters and meters has 10 to the negative 2 meters equals 1 centimeter. But I can also see that, notice I have 1 kilometer, so I can put that here. Oops, I'll put it in purple like I was doing before. I can take the kilometer, which is on the left-hand side of the base, and I can put a 1 with it. And then I can say that's equal to, and I notice the kilometer actually has times 10 to the third, so I'm going to put 10 to the third and then put a meter on it. So that's the conversion, or that's the equivalent statement between kilometers and meters. So now I can do this. I'm going to say 1 centimeter. What we know is from this, 1 centimeter is 10 to the negative 2 meters. So I'm going to say 1 centimeter is 10 to the negative 2 meters. And we hadn't used that top left, bottom right slash before, so I'm using that now. Now I'm up to meters per hour. And now I'm going to go from meters to kilometers. So what I know, if you look back here, is that 1 kilometer is 10 to the third meters. So I'm going to say 10 to the third meters, which by the way is 1,000 meters, is equal to 1 kilometer. And now I've used up all those different ways of doing straight lines, and I've used one of the curved lines, so I'm going to use a different curved line to mark out the meter here. I'm going from bottom left to top right like that. And you see that now I have specifically only the units of kilometers in the numerator and the units of hours in the denominator. So again, like I told you before, you multiply all the numerators together, and that's your new numerator. So I'm going to say 60 times 5280 times 12 times 2.54 times 1 exp to the negative 2 times 1, and that gives me 96,560.64. And remember, doing that is just basically making sure I use all this information I have. In other words, I don't have to have that many sig figs on the miles per hour that I put in to get it out. This is all coming from the 5,280, the 12, the 2.54, the 10 to the negative 2, and the 1 and the 1,000. So it just has to be true that way. Now I'm going to take all the denominators, which is 1 hour. Oh, the top turned out to be kilometers, so I put a kilometer up there too. So the bottom turns out to be a 1 hour times 1 times 1 times 1 times 1, and then times 1,000. So this is going to be 1,000 hours on the bottom. And now you can see that that's just going to move the decimal 3 places to the left, and the answer is going to be 96.56064 kilometers per hour. And that is the equivalent of 60 miles per hour. Now, we only had 60, assuming that's two sig figs. We only had two sig figs that we put in. That means beyond two sig figs is not actual significant figures. So this 5, the 6, the 0, the 6, and this 4 is not significant. So basically, what we know is 60 miles per hour is about 97 kilometers per hour. Which they also write that as kph. So that helps. Now, what I'm going to do is the same thing, but this time I'm going to convert it to meters per second instead of kilometers per hour. So let me go ahead and carry that out. So we've got 60 miles divided by 1 hour. Switching to my red, I'm going to do the same thing I did before. I'm going to say 5,280. This time I'll actually write out the feet. 5,280 feet equals 1 mile. That cancels out with that. And now I'm going to say 12 inches is equal to 1 foot. And this foot will cancel out with that. Notice I used bottom left to top right for miles, and I used top left to bottom right for feet. So I am keeping up with my bookkeeping method. And I'm now in feet per, or excuse me, in inches per hour. And now I'm going to go from inches to centimeters. So I'm going to say 1 inch in the bottom, 2.54 centimeters in the top. And now I'm going to use a complete X to cancel out the end. Now I've used up sort of all my straight line X versions. So I'm going to start doing some curvy stuff next. That gets me to centimeters per hour. And ultimately, I want meters per hour. So now I'm going to say times what I really know. And I wouldn't even use the 10 to the negative 2 normally. I was just doing that to show you how. What I know is 1 meter is equal to 100 centimeters. So what I'm going to say is 100 centimeters in the bottom is equal to 1 meter on top. And I am going to do a top left, bottom right curve, top left, bottom right curve to get rid of centimeters. Now I'm up to meters per hour. Now I'm going to skip the two-step process because I could go from hours to minutes with a 60 and then go from minutes to seconds with another 60. I'm just going to jump straight to the seconds by using 3600. And what I'm going to do is say that 1 hour, which has to be on the top because the hour that we're trying to get rid of is on the bottom. So I'm going to say 1 hour is equal to 3600 seconds. And now I can do a bottom left, top right curve to cancel out the hours, and that works perfectly. So now, as I told you before, I'm going to multiply all the numerators to get a new numerator, and then multiply all the denominators to get a new denominator. So I'm going to take 60 times 5280 times 12 times 2.54 times 1 equals 96. Ooh, this is a much differenter number. So this is 9,656,000 64. And that top unit is a meter. And then the bottom is 1 times 1 times 1 times 100 times 3,600. So that's going to be 360,000, and that is just in seconds. And now we're going to take and divide the numerator by the denominator to get the new number. So I'm going to take the 99,656,064 and I'm going to divide it by the 360,000 that I have in the bottom, and that gives me 26.8224 meters per second, but I only use two sig figs. So technically speaking, the 8, the 2, and the 4 are not sig figs. And that is 60 miles per hour, and meters per second is about 27 meters per second. Any questions on that one? All right, it's been an hour, so I'm going to go ahead and give you guys a 10-minute break. It's 6:38 right now. Come back by 6:48. I'm going to be here. If anybody has any questions, you can ask them. But I want you to go ahead and get you a little break in. So I will start back up at 6:48. I'm good, baby. Thank you. Got about 5 more minutes left, folks. Got about 2 minutes left. Looking about like it's time to go. Just a second. All right, so let's go ahead and get started. Looks like everybody's mostly back anyways. Go ahead and chat me your first and last name. I will use that for a roll. If you're not from PHY 241N02B, just put like your section number. You can just say asynchronous, or you can type in 001B next to your name. But the main thing is give me your first and last name. And if you're in a class other than the one that's supposed to be meeting today at 5:30, then just put a zero, or excuse me, 001B or asynchronous or something like that after it. What I have is another type of conversion that I need to teach you guys. Specifically, what do you do when you have units like cubic meters or square kilometers or square grams or something like that? There's a very specific process that has to happen. And as you can tell, in this particular example, I'm going to use the density of water to help us with that. So this will work when you're talking about, square footage of a house and you want to convert it from square feet to square meters or stuff like that. But it also works when you later find out there's equations that sometimes have things like distance raised to the third power or distance raised to the one-third power, weird stuff like that. So what I'm telling you is the density of pure water is about 1,000 kilograms per cubic meter. That's specifically, if I remember correctly, that should be at 20 degrees Celsius. Might be at 0, but I think it's 20 degrees Celsius. And that's kilograms per cubic meter. Remember, a kilogram's about 2.2 pounds. So when you say 1,000 kilograms, that's what we call a metric ton. And you can see that it is sort of a ton, because if you recognize what a ton is in America, we use a ton to be 2,000 pounds. This is a metric ton, which is a little bigger than a ton, and you see it's 2,200 pounds. So that's the difference between a metric ton and a ton. A regular ton is also sometimes called a short ton, but that's kind of interesting. Just know if you have a box of water that is about 39 and an eighth inches by 39 and an eighth inches by 39 and an eighth of an inch, then that should weigh essentially a metric ton. So that gives you some appreciation for how heavy water is. You've probably seen these cubicle water containment systems that have been sitting in the back of trucks or sitting in the back of trailers and stuff like that. Those are essentially a cubic meter of water. So just imagine those people moving those things around. They're actually dealing with a whole 2,200 pounds of water when it's full. Now, with that in mind, it says, what's the density in grams per cubic centimeter? And what's the density in grams per milliliter? And what's the density in kilograms per liter? And I said, note, a liter, 1 liter, is defined to be the volume of a 10 centimeter by 10 centimeter by 10 centimeter cube. So I'm going to use that to make some sense of what a liter is. So let me start off by doing that. I'm going to say 1.0 liters equals 10.0 centimeters times 10.0 centimeters times 10.0 centimeters, which is equal to 1,000.0 centimeter times a centimeter times a centimeter is a centimeter cubed. So you can see that 1 liter equals 1,000 cubic centimeters. That also means that 1 milliliter, which equals 1 times 10 to the negative 3 liters, which equals 1 times 1 over 1,000 liters. So a milliliter is 1/1000th of a liter. with that in mind, you can realize that 1.0 milliliters is exactly equal to 1.0 cubic centimeter. And that's a fundamental idea that you sort of need, especially going, into adulthood, because inevitably what's going to happen is many people end up having children. And when you have a child, you're going to go to a doctor at some point. And when you go to a doctor at some point, they're going to write a prescription for you in cc's, and then the pharmacist is going to fill it in milliliters. And you're going to flip out because your baby has a prescription that's in different units that you remember the doctor putting down. So you're kind of freaking out. But hopefully you'll remember this. 1 cc, which is abbreviation for a cubic centimeter, is the same as a milliliter. Okay, so just keep that in mind. That'll be coming in handy several times throughout your physics course. So let's start off with part A. Part A, I have the density of water. There's the Greek symbol rho that we use for the density of water. That's going to be 1,000 kilograms. And remember, we always started off by writing it as a fraction. So I just went ahead and wrote 1,000 kilograms over 1 cubic meter. And what we want to do is convert that to grams per cubic centimeter. So I'm going to show you how to do that. What we know is that 1 kilogram is 1,000 grams. So I can put 1 kilogram on the bottom and put 1,000 grams on the top. And what will happen is that kilogram will cancel out with that kilogram. And now I have 1,000,000 grams per cubic meter. Well, that's good because I've now converted to grams, but I need the bottom to be in cubic centimeters. So what I'm going to do now is I'm going to realize that 1 meter is 100 centimeters. So I'm going to write 1 meter on the top and 100 centimeters on the bottom. And what you can see is the meter is going to cancel out one of the exponents on the cubic meter. So instead of it being a cubic meter, it's going to be a centimeter times a meter squared. Well, I do it again, and then that'll make it 1 meter times a square centimeter. And then I do it again, and that'll make it 1 cubic centimeter, period. So that's how you deal with an exponent of 3, is you do the conversion 3 times. What we can see now is that this meter is going to cancel out with this meter, and this meter, specifically because it went through all 3 of the exponents, basically the exponent being 3. So there's 3 of them there. So now you can see that 1,000 times 1,000 is 1,000,000, but 100 times 100 times 100, oops, that's supposed to be 100 in that last one. 100 times 100 times 100 is also 1,000,000. So what we end up getting here is 1,000,000 grams divided by 1,000,000 cubic centimeters, which means the density of water, which equals 1,000 kilograms per cubic meter, is also equal to 1 gram per cubic centimeter. So that's our answer to A. Anybody have any questions with that? Okay. Now we're going to do part B, which actually is a lot easier since I did that first part. What we discovered in that first part is that 1 milliliter is equal to 1 cubic centimeter. So if I want to do part B, all I have to do is say B, the density of water is equal to 1.000 grams divided by 1.000 cubic centimeters. I just wrote 0.000. I don't even know why I did it. I just did it. So let's just ignore that and move on. Sorry, these are the jokes. This is all the fun you get from fat physicist working on Wednesday night. All right, now that we have that, what we know from the little red part we did after the explanation of the extra credit is we know that 1 milliliter is equal to 1 cubic centimeter. So I'm going to write 1 ml in the bottom, and I'm going to write 1 cubic centimeter in the top. And you can see that this cubic centimeter is canceling out with this cubic centimeter. And lo and behold, I get a really nice result. The density of water, which equals 1 gram per cubic centimeter, is equal to 1 gram per milliliter. So that's another result we were asked for, and that's kind of nice. And finally, what we're going to do is figure out how to convert this to kilograms per liter. So what I'm going to do is start off with part C. I'm going to say the density of water is equal to, since I want it in kilograms, I'm going to go ahead and do 1,000 kilograms on the top, and that's 1 cubic meter on the bottom. But I want to convert that to liters, and what I know is 1 liter is 1,000 cubic centimeters. Another thing we can figure out with the liter is we can say that 1.0 liters is equal to 1,000 cubic centimeters. And if I want to try to convert that to cubic meters, what I can do is say, all right, let's put this over 1. Actually, I didn't mean to undo that. I'm going to put that over 1. I'm going to put this X at a little better spot. And now I'm going to say 100 centimeters is equal to 1 meter. And then I'm going to cube that. By cubing it, I'm doing the same thing as I did before. I'm getting rid of each of the centimeter factors. There's a centimeter times a centimeter times a centimeter. So this centimeter cubed is going to cancel out with this centimeter up there. It'll still leave the meter cubed, but what we're going to see is that I'm taking 1,000 and dividing it by 1,000,000. So the answer is going to come out to be 1,000 over 1,000,000, and that's cubic meters in the numerator. So what we see is it is 1/1000th of a cubic meter. So this liter is the perfect thing. It's dead center between a cubic centimeter and a cubic meter. In fact, it's 1 liter is 1,000 cubic centimeters, but 1,000 liters is a cubic meter. So that's what we've discovered is 1,000 liters is equal to 1 cubic meter. So now I'm going to make use of that. I'm going to say 1,000 liters is equal to 1 cubic meter. You can sort of think of it as a milli-cubic meter is a liter. But you can see why I don't say that, because it'd be like m space m cubed, and that looks like a millimeter cubed, and that's not what we want. But that actually does it. Now I can see that the meter cubed is going to cancel out with the meter cubed on top. I can also see that the 1,000 divided by 1,000 is going to give me 1. So lo and behold, what we get is that the density of water, which is 1,000 kilograms per cubic meter, is also equal to 1 kilogram per liter. So it's really nice that pure water has a density that's essentially 1 in so many different units. That's why I mentioned in purple here, it says there is an extra credit assignment that continues investigating the density of water. See extra credit 1, so it's in parentheses EC1, extra credit density of water. It's in the week 1 module of your Canvas page. So if you want to do that, you can do it. What it does is it converts it to some other systems of units. For instance, if you ever taken a scuba diving class, there's a specific density of water that they use there. That one's is one of them is for pure water, which would be fresh water. But if you, instead of using 1,000 kilograms per cubic meter, if you use a 1,025, that's essentially a good estimate of the density of salt water. And then you can get the values that they use for salt water in scuba diving classes as well. So anyways, give that extra credit a try if you want. Again, it is an extra credit, so it doesn't matter if you try it or not. But if you do try it, you can, help your grade a little bit. Anybody have any questions on that? All right, I did ask everyone to go ahead and chat me your first and last name. It looks like y'all did that, but I'm just reminding you in case you weren't here when I said it. Remember, if you're in this class, the N02B, you just chat me your first and last name. But if you're in the other class, the O01B, chat me your first name, first and last name, along with the 001B or with the word asynchronous or something. Let's move on now, and we're going into chapter 1 on the section that they call rapid estimation. These are also called Fermi calculations, Fermi, which if you've ever heard of the place Fermi Lab, that's where that came from. It's named after a man by the name of Enrico Fermi. And Enrico Fermi was a Italian physicist and Nobel laureate that, thank God for the Nobel Committee, he was able to win the Nobel Prize, and he was working under Mussolini at the time, and he had just established a really first-notch physics program in Italy, which it hadn't had in a long time, and he was very well respected, and he won a Nobel Prize, and Mussolini wanted to show how his system of government, which seems a little bit like a fascist system of government at this point, he wanted to show how that was superior to all the other ones. So he obviously wanted Enrico Fermi to go and get the Nobel Prize. Enrico Fermi said, "Well, I'd like to bring my family." And Mussolini said, "No, we're not going to let you do that for obvious reasons." Namely, they're afraid he's going to run away. He said, "Well, then I'm not going." So they reneged and basically said, "Okay, I'll allow it." And they let him go. And soon as he got away, he went ahead and him and his family defected, ultimately defecting to America. And he became a professor at University of Chicago. And under their football field, he basically made a nuclear reactor. It was the first self-sustaining nuclear reactor ever, or self-sustaining nuclear reactions that have ever been created. And he sort of is the brains behind the Manhattan Project. So if you've seen the movie Oppenheimer, J. Robert Oppenheimer played a big role, and a bunch of other really huge brains in physics played big roles. Richard Feynman, uh, darn it, I'm drawing a blank on virtually everybody right now. But anyways, a lot of people were there. Niels Bohr came by. Niels Bohr's son, Aga Bohr, came by. Various other people. But the main thing is the guy that was sort of feeding them the knowledge at the time was really Enrico Fermi. So it's kind of a neat little story. But anyways, he has this reputation of being someone that can calculate anything. Like he could, like in 2 seconds, tell you how many piano tuners there would be in the whole state of California or in the city of San Diego or something like that. All sorts of weird calculations like it. So what I wanted to do for you is take one of these estimate type calculations and give you an example of one. So what I saw, it was on, I want to say it was on Instagram, but it might have been on TikTok. I can't remember, but someone who made a ton of money, lived in a really nice house, way nicer than I have, with a really nice Lamborghini, which is way better than what I have, had made a lot of money by doing stupid videos. And in this particular video that I watched, he was filling up a shower stall with Fruit Loops. And it aggravated me because he kept having to go back to the store and buy more Fruit Loops. And I'm like, any goober can estimate how many Fruit Loops is going to take. So I thought I'd do that. But instead of Fruit Loops, let's think of fruit flies, or, basically house flies. So how many house flies do you believe could fit in this shower stall that you see in this photograph here? Now, I'm imagining it as if it has a lid. So let me show you what I mean by this. So I'm imagining that this is like a lid. In other words, I only want it this deep. like that. So that's the lid. And then, of course, there's also a face right here. So I just want to know roughly how many houseflies you could fit in the shower stall. So to do that, you've got to have some understanding of what the sizes of things are. And specifically, we want to know those sizes in the metric system units. So I will tell you, for instance, that a meter, which I already hinted to, is about 39 and an eighth of an inch, roughly, if I remember correctly, the eighth of an inch part. I know it's a little bit bigger than 39 inches. And I want to say it was pretty close to like an eighth or 3/8 of an inch. I can't remember, but it doesn't matter too terribly much. So that also happens to be about the height of a doorknob. So that's what a meter is. A centimeter is the width of my pinky nail. You might say it's probably the width of, especially if you're a smaller person, you might find that the width of your index finger nail is a centimeter. Or if you're a slightly bigger person, you might, or a slightly smaller person, you might find that your thumbnail is the width of a centimeter. Another thing that you could use is the width of a staple, like a typical staple you'll have at the front of your classroom. That's usually a centimeter wide and it's about a millimeter thick. So that can give you some ideas. What I'm looking at right now, it looks like a shower stall, and I'm going to ignore this little hump right here. I'm going to ignore that hump and just assume that it's sort of an empty little box. The whole shower is an empty box. So we're picturing that the shower is more like this shape. Now, that's not necessarily a good approximation since that big platform or seat is there, but we can use it as a first order approximation. And then we can estimate the size of the box and add that many fruit flies to fit in there if you want. So now looking at this box, I'm going to say that this distance is about 2 meters. I'm going to say that this distance in and out of the page is about 1 meter. It's probably a little less than a meter, but that's okay. And I'm going to say that this distance from here to here, I'm going to say that is on the order of, oops, that's also on the order of 2 meters. Okay. So I can say that the volume of the shower, I'll go ahead and write the question here. So notice how I'm actually estimating the size of it in the metric system. That's something you got to be able to do. So you got to get used to that and learn how big a centimeter is, how big a meter is, how big a kilometer is, how big a millimeter is, that sort of thing. And you got to have some idea of how big a fruit fly is. So I'm going to say a fruit fly normally looks something like this. And I'd say this fruit fly, maybe its length is on the order of, I don't know if you look at it, I'd say it's smaller than a centimeter. So I'd say about 9 millimeters would be that dimension. I would say this dimension, height wise, is probably 3 millimeters. And I'd say the width of the fruit fly, ignoring the wings, you just assume the wings are attached to its body or its thoracic cavity or whatever. I'd say that width is also about 3 millimeters. That being said, don't let your knowledge of how big the thing is completely prevent you from doing the calculation. What you can do is you can think of a unit that you know it's smaller than, and then you can think of a unit that you know it's bigger than, and then you can take the geometric mean of the two, and that'll give you an estimate of roughly how big that dimension is. So for instance, if I had no clue about the length of that fly, I would say, well, that fly is, it's definitely smaller than 2 centimeters, but I'd say it's also definitely bigger than a millimeter. A millimeter, of course, is a tenth of a centimeter. So what I could do is I'd say length of a fly is less than 2.0 centimeters, but bigger than maybe I'd say 2 centimeter or 2 millimeters. Okay. If I did that, then I'd say L is approximately equal to the geometric mean. And what I'm going to do is I'm going to put the geometric mean, both of the numbers in the same unit, specifically millimeters. So I'm going to say 2 centimeters is 20 millimeters times 2.0 millimeters, like this. And now I can take 20 times 2, which would be 40, of course. And that's 40. Now I'm going to take the square root of that. And the square root of that is about 6.32 millimeters, which is pretty decent. And what we do when we're doing these estimates is we pretty much only use one sig fig. So I would say this is approximately 6 millimeters for the length. That's pretty good. I call it at 9. There are certainly flies that are only about 6 millimeters long. That's certainly okay. And we're only looking for an estimate, so that's certainly fine. So what I'm going to do is first I'm going to calculate the volume of the shower. And the volume of the shower, since it's rectangular, is length times width times height. Not necessarily having a good definition of length, width, and height. You're actually allowed to use any one of them as the length, and then any of the other ones as the width, and any of the remaining ones as the height, and that'd be fine. So that's what I'm going to do here. I'm going to say it's 2 meters times 2 meters times 1 meter, which gives me 4 cubic meters. Now, ideally, I would like that in millimeters because I have all the fly dimensions in millimeters. So I either need to convert the fly dimensions to meters, or I need to convert the shower dimensions to millimeters. I'm going to choose to put the shower dimensions in millimeters. So what I'll do is I'll write this 4 meters cubed. I'm going to put it over 1. And what I'm going to do is I'm going to say that 1 meter is actually equal to 1,000 millimeters. But the meter's actually cubed, so I've got to do that conversion factor 3 times. So I've got to multiply it by 1,000, by 1,000, and by 1,000. That's literally multiplying by a billion. So the answer is going to come out to be 4 times 10 to the 9th cubic millimeters. So now if I want to estimate how many flies go into it, the number of flies is N, and that's going to be the volume of the shower divided by the volume of the fly. So the volume of the shower we just found was 4 times 10 to the 9th cubic millimeters. And the volume of the fly is going to be 3 times 3 times 9. 3 times 3 is 9, times 9 again is 81. So I'm going to divide it by 81, excuse me, cubic millimeters. So 4 times 10 to the 9th divided by 81 gives me 4.9. Whoa, Nelly. Times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th flies. So what I'd say is N is approximately equal to 50 million. So that's a way of estimating uh, something like the number of fruit flies that'll fit in a shower. Fruit Loops could be done the same way. Of course, then you'd have to figure out roughly how many Fruit Loops come in a box. You could do that by weighing one Fruit Loop and then, taking the weight of the Fruit Loops and dividing it by the weight per Fruit Loop, and that'd give you roughly how many Fruit Loops are in there. And then you basically just buy the appropriate number of boxes of Fruit Loops and fill up the shower, no problem. Okay, so you wouldn't have to go back and forth like the guy did on TikTok. If you did want to go back and adjust it to account for that seat inside the shower, then what I'd probably do is say that uh, maybe the height of it's about 0.7 meters, and the width in one direction is about 0.8 meters, and the width in the other direction is about 0.8 meters. And then I just basically take that 0.8 meters times 0.8 meters times 0.7 meters and calculate that volume, and then divide it by the volume of the flies and subtract that from the 50 million. Okay. Any questions on that? Another thing that we often do is, as you'll see in example 5.1 of your book, if a pond looks sort of circular, treat it like a pond, treat it like a circle. Okay. If you don't know how deep it is, but you know roughly how deep it is on average, treat it as if it's the same depth as the average, and it's that depth all around. So you can do it like they did in exercise estimate exercise and excuse me, too many E words here. Example 1-5, an estimate problem. So you can look at that one for it. There's other neat little problems you can do. For instance, let's say you walk up. This is kind of a neat project. Let's say you have a building right here, and you'd like to know the height of the building. But what you do is you walk up to it, and you see that right here is a sign, and you stand right there by the sign and look up in such a way. Excuse me, let me draw this a little taller. Let's draw this a little taller. And you look up in your line of sight until you hit just the top of the pole. And by doing so, it runs right into the top of the building. Okay. Now, what you might realize is that this distance, the height of that pole, is 3 meters. You also might realize that your eyes are about 2 meters high, or maybe actually that's not that good, because that normally for your eyes to be 2 meters high, you pretty much have to be 6'3" or so. So that's a little less than normal, or a little taller than normal. So it's probably not reasonable to say that. I'm going to say your eye height is 1.5 meters, and let's assume this distance from here to here is 2 meters. Okay. So what you could do is walk off this distance, figure out what that is, because then you'd have an actual triangle that's this, and that can allow you to figure out exactly how tall the building is. You'll have to add, obviously, this 3 meters, you'll have to add that to it once you get this particular distance, which is a question mark. But you see, there's actually two similar triangles here. There's the triangle that goes from your eye horizontally to the top of the pole. And then there's a triangle that goes from the top of the pole to the top of the building. So the fact that it's two similar triangles, this one has a length of 2 and 1.5. This one has a length of question mark. And let's say we walk this distance off, the distance right here. We walked it off. We took sort of broad steps, so it felt like we were maybe taking 1 whole meter footsteps. If I did that and I found that the distance was about 15 meters, then I could say this distance right here is 15 meters. So the question was estimate the height of the building. Okay, so you want to estimate the height of a building. We're going to do that now. Using similar triangles, what I see is 2 is to 1.5 as question mark. Ooh, excuse me. 2 is to 1.5 as 15 is to question mark. That's the ratio of the common or the similar sides. So the 2 side is similar to the 15 and the 1.5 is similar to the height part of the triangle. So we can use this ratio, this proportion, excuse me, we can use this to solve for question mark. And all we have to do is cross multiply. This is the only time, by the way, you cross multiply. Don't get in that rut of thinking you cross multiply to work with fractions. That's not it. Uh, but 15 times 1.5 is 22.5. So I'm going to say 22.5 meters, and that's actually meters squared, is equal to 2 times question mark. So that means question mark is equal to, and 2 is in meters, by the way. So question mark is 22.5 meters squared divided by 2 meters. And that gives me 11.25 meters. So I now know that this height is 11.25 meters roughly. We're going to do all this in one sig fig in a second. But now to find the height of the building, I actually need to add the 3 meters to it. So I'm going to say H is approximately 3 meters plus 11.25. So I'm going to call this approximately 14.3 meters. And that's a way of approximating the height of a building. Another way is if you have a good feel for exactly what 45 degrees is. Remember, if you're looking 45 degrees up, horizontal 0, straight up, which is really hard and painful to do, that's 90. But if you go dead center between the two, you should be at 45. So if you can figure out roughly how your head's supposed to be tilted when you're at a 45-degree angle, then you could walk to the bottom of the building out until you look up at the top of the building and feel like your head's looking up at 45. And whatever distance you walked away, since it's a 45-degree triangle, is the same distance above your head to the top of the building. So that's another way of doing it. Anybody have any questions on that? Another thing I've done in my classes before, your book does an example sort of like this. One thing I often do is I'll take our Giancolli's textbook and I'll just lay it in the front of the classroom. And I'll say, Giancolli's book has 1,376 pages. How thick is a page of Giancolli's textbook? So that's another type of problem where you would look up at the actual Giancoli textbook and you'd make an estimate of how thick the pages are. And you'd obviously want to make that in centimeters or millimeters or meters or something. And then you'd say, okay, well, wait a second. If it has 1,375 pages and that thickness is, let's say, 2.5 centimeters, then the thickness per page would be 2.5 centimeters divided by the number of pages. But remember, each page has 2 sides, so you'd have to not divide it 2.5 centimeters by 1375. You'd have to divide 2.5 centimeters by half of 1375. And then that would give you a pretty good estimate of the thickness of a single sheet of paper. That's a very typical estimate type question. Anybody have any question on that one? I'm just double checking something real quick. Let me pull this up just to see. All right. So now that we have that, you've seen a couple different ways of making estimates, stuff like that. Uh, Another one your book does, this is kind of neat. I think I'll do this one. Uh, Estimate the radius of the Earth and we're going to do it in a very specific way. I'm looking at example 1.9, so you can refer to your book on this, but I'm going to read it. It says, actually, let's do this. I'm going to stop sharing for a second, and I'm going to share again. This is kind of a neat problem. So now I'm going to do, where did my, oh, here it is. Now I'm going to do share this screen right here. So it says, believe it or not, you can estimate the radius of the Earth without having to go into space. See the photograph on chapter 1. If you've ever been on the shore of a large lake, you may have noticed that you cannot see the beaches, piers, or rocks at water level across the lake on the opposite shore. The lake seems to bulge out between you and the opposite shore, a good clue that the earth is round. Suppose you climb a step ladder and discover that when your eyes are 10 feet, which is about 3 meters above the water, you can just see the rocks at water level on the opposite side of the shore. From a map, you estimate the distance to the opposite shore to be 6.1 kilometers. Uh, Use that to determine the radius of the Earth. So that's what we're looking at. So we look at a h equal to 3.0 meters, and we look at a L, or let's say, yeah, I'll say an L as equal to 6.1 kilometers. Now I'm going to draw what we mean by that. So I'm going to show a section of the Earth. And what we're looking at here is we're imagining a pond or a lake, something like that, right here. And we know that perpendicular to the Earth at that particular spot is the actual radial line for the Earth. And then perpendicular to the other side is, of course, also the radial line to the center of the Earth. So what we see is this distance is r, the radius of the Earth, and this distance is r, the radius of the Earth. What we also see, though, is that this distance, which is sort of curved, but is also sort of straight because it's,
Excuse me.
yes. Oh, yeah.
Sorry. Yeah, we can't see your screen.
I forgot to show you the iPad. Yes, that would be helpful. So now that y'all have seen that, let's go ahead and share the appropriate screen since Mr. Younger's obviously been drinking before class or something crazy. Let's stop sharing. Here we go. In here and there and there. Thanks for catching me on that. That is a mistake I occasionally make. So please, by all means, feel free to correct me whenever I screw up like that. So this is the drawing I have. It should pop up. There it is. So there's the drawing I have. The purple line is the surface of the Earth. And then this is supposed to be the lake. And this length right here is the L that we're talking about. Okay. Now, the other thing is that we're going to take a line perpendicular to the radial line and follow that straight back like this until it runs into this other radial line, because basically that right there is the height h that you had to climb up on the step ladder to see the rocks on the other edge of the lake. And this length is L right here, meaning that little horizontal length along the water is L. So if you look at this, what you realize is that even though it doesn't look very square, it really should be. This should be a right angle. So we have a right triangle right here. And according to the Pythagorean theorem, what we know is one leg of the actual uh, right triangle is this one right here. And then another leg of the right triangle is this one right here. This one's actually the hypotenuse though, and that distance is r plus h. So what we can do is using the Pythagorean theorem, we can say r plus h squared is equal to r squared plus, now here's the kicker, you need that other length across the lake. Now, this triangle is really blown way out of proportion. In all honesty, this little angle that we're looking at right here, that angle is super, super, super small. So it'd be more realistic to look at this triangle as if it were like this, in which case you would think that this length and this length are about the same. So that's what we're going to do. We're going to, even though we know L is really the red line, it's so close to the other line that we're going to say this is approximately equal to L. So I'm going to say this length is approximately equal to L. So we now have r plus h squared, which is the hypotenuse, is equal to r squared plus L squared. And we can go ahead and square this binomial. That becomes r squared plus 2hr plus h squared is equal to r squared plus L squared. We know L, we know h. The only thing we don't know is r. The good news is we can subtract the r squared from both sides, so at least we don't have to deal with the Pythagorean theorem or a quadratic formula that we have to use. Now we've got r uh, as the only unknown in here. So what I'm going to do is pull the h squared to the right-hand side. That's going to give me 2hr is equal to L squared minus h squared. And then that means r is going to be L squared minus h squared over 2h. So we can plug those numbers in. I'm going to keep them all in meters, so that 6.1 is going to become 6.1 times 10 to the third meters. Then I got to square that, minus 3.0 meters squared. All that divided by, and there's a decimal there, 2 times 3.0 meters, like this. So when I do this math, I get 6.1 times 10 to the third squared minus 3 squared. And that gives me 3.72 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th meters squared over 6.0 meters. And that gives me 6.2 times 10 to the 6 meters. So what we've just found is that the radius of the Earth is about 6 million meters. Now, you could also call that 6,200 kilometers if you wanted to. Either one of those are acceptable. That's really fairly close to the Earth's size. The actual Earth's size is 6,000, or excuse me, 6.38 times 10 to the 6 meters is the real radius of the Earth. And this is the symbol they use for the Earth in astronomy, by the way. So that's not too terribly far off. Of course, that probably took the author a little bit of time to find a lake that was roughly the right size, or he might have just worked it backwards to figure out exactly what size the lake needed to be and what height the height had to be and that sort of thing. But either way, it's pretty remarkable that you can get that good of a result. Not unlike what Eratosthenes did with a vertical pole and estimating the radius of the Earth. Anybody have any questions on that? All right, so that's another estimating type problem. I want you guys to go ahead and look at all the estimate problems that they do in chapter 1. They're all really good. What you'll see though, when you start taking your practice test, is you'll run into problems like how many times should a human being's heart beat in a lifetime? So one particular human being, about how many times will his heart beat in his whole lifetime? That's an estimate you should be able to make. You have to use things like estimate how long a human lives, estimate how many beats per minute a heartbeat is, figure out how many minutes there are in a year, that kind of thing. That's one of them. Another one is a shoebox, and they give you sort of the dimensions of a shoebox and ask you how many pennies you could stack in that shoebox. Or how tall would a stack of $100 bills equaling $1 million, how tall would that stack of $100 bills be? All of those are typical examples that you should be able to figure out. So by all means, you might want to start at least doing chapter 1. If you look, there's some chapter practice in your Canvas page, and that chapter practice isn't like the practice test. It's just a single quiz for each chapter. So right now you've only finished chapter 1, or you've almost finished chapter 1. So you can start doing that. And once you start getting into chapter 2, maybe you can start taking the practice test. But until then, you can start taking the chapter 1 quiz if you want, and just do that over and over to get some practice. Right now, we're going to move on to the last section, which is dimensions, dimensional analysis, and unit analysis. So one thing I got to tell you guys is that when you write an equation like A equals B, there's more to it than just A equals B. When you say, a certain number of miles per hour is equal to a certain number of miles per hour, not even talking about vector quantities, which we haven't gotten to yet, but just talking about numbers in general, it's true that not only do the numerical parts have to be equal. So if you say A equals B, A's got a numerical part and it's got a unit part. B's got a numerical part and B's got a unit part. In order for A to equal B, the numerical part of A has to equal the numerical part of B, and the unit part of A has to equal the unit part of B. So you've got to keep that in mind. But once you have that down, then you can do a lot of powerful things. So for instance, let's try this one. Let's say, assuming energy is dependent only on the speed of light and mass, postulate and our A formula for energy E in terms of mass M and the speed of light C. Note, when I write a variable like E inside of a square box like that, that means I'm just asking for the units or the dimensions. I haven't taught you what I mean by dimension yet, but they're closely related to units, okay? So whenever I write something in square brackets like that, I'm saying, hey, let's forget about what E is. Just tell me what the units are, or tell me what the dimensions are. The units for energy is technically the joule, and a joule is a Newton meter, and a Newton is a kilogram times a meter per second squared. And then, of course, that's times a meter. So you can see that the units for the energy are kilograms meters squared divided by second squared, which you can also write as kilograms to the 1 power, meters to the 2 power, and seconds to the negative 2 power. Okay. Now, if that was all units, now what do I mean by dimensions? So with dimensions, let me show you what I'm going to do now. I'm going to go ahead and use the result that I found already, that namely it's kilograms to the 1 power, meters to the 2 power, and seconds to the negative 2 power. And what I'm going to say is the dimensions are m to the 1, L to the 2, and capital T to the negative 2. Can y'all see what I mean by dimensions now? Do y'all think that makes some sense? The unit of a kilogram is a unit of mass, so we use a capital M to represent mass. The unit of a meter represents a length or a distance, so we use a capital L to represent it. And the unit of time is represented by seconds, and we use a capital T to do that. So this is how we're going to find an equation. What I'm going to say is formula, hypothesis. So I'm hypothesizing that the formula for the energy is equal to mass to some power p times the speed of light to some power q. Okay. Now, because we were only told it depends on mass and the speed of light, that's the only two variables I should have in there is m and c. And you can't add M and C together because they have different units. You can't subtract M from C or C from M because they have different units. All you can do is multiply M times C or divide M by C or C by M, or some powers of M and C can be multiplied or divided. So that's the most general thing I can possibly do, is say that energy is equal to mass raised to the P power and speed of light multiplied by that, but raised to the Q power. So now what I'm going to do is use that and figure out what P and Q are, and that should give me a formula that relates energy to mass and the speed of light. So the energy, if I talk in terms of units, are dimensions. Like this, then that means energy, which has kilograms to the 1 power, meters to the 2 power, and seconds to the negative 2 power, is equal to, now here's the other part, the velocity or the mass should have units of just kilograms. So I can say kilogram, oops, might as well do it right. I can say kilograms raised to the P power. And the speed of light, you probably already knew speed of light is distance per time, so it's meters per second. So what I'm going to do is I'll put meters over seconds here, and I'll raise that to the Q power. Do you see how that relates to the E equals M to the P, C to the Q? Everybody see how that works? So now all I got to do is figure out a P and a Q that makes all of this true. So I've got kilograms to the 1 power, meters to the 2 power, seconds to the negative 2 power. I've got kilograms to the P power. I've got M to the Q power. And I've got S, since S is on the bottom, that's actually to the negative Q power. Does that make sense to everybody? Anybody have any questions on that? So we can immediately see that P only occurs on the kilograms. So this immediately tells us that P is equal to 1. All of them have to be true though. So we're saying P equals 1, but we might find it's impossible. We might not find any Q's that give the right answers. Now, what we do have is is raised to the 2 power, and on the right-hand side, it's raised to the Q power. So that would also suggest Q is equal to 2. Well, that fixes the meters, but now we have to check with the other part, which is, in this case, we actually did with the mass, but now I'm going to do it with the second part. So S is raised to the negative 2, and negative Q is evidently equal to negative 2, and that means Q is equal to 2. And we see that by doing this, I've found no contradictions with each other, and it does seem to work. So guess what? Our formula for energy is E equals m to the first power times c to the 2 power, which means E equals mc squared, which is exactly the equation that Einstein came up with. Now, I could have also done that with dimensions. If I'd done it with dimensions, it would look like this, and then I'll let you guys go. So with dimensions, I'm going to say on the left-hand side, we have oops, there we go again. We have m to the 1 power, L to the 2 power, T to the negative 2 power. And then on the right, we have m to the P power, and we have L over T, which is the units for, or excuse me, the dimensions for speed. They're raised to the Q power. So that means M to the 1, L to the 2, T to the negative 2 is equal to M to the P, L to the Q, and T to the negative Q. Again, we find P is equal to 1, Q is equal to 2, and negative Q is equal to negative 2, which also implies Q equals 2. So we get E equals mc squared. So that's it. That's the big trick with dimensions and unit analysis. So you can use it like this to actually come up with an equation. For instance, you can say, hey, another quantity called energy, specifically kinetic energy, is related to mass and velocity. So you could write K equals m to the P power and V to the Q power, and then use your units for K, use your units for M, use your units for V, and find out a formula for that. In that case, you'd actually come up with the wrong answer, but it'd only be off by a factor of 1/2. So you'd end up getting mv squared instead of 1/2 mv squared, because you guys might recall, if you've ever had any physics before, that kinetic energy is 1/2 mv squared. But that's it. We've now completed chapter 1, all of chapter 1. You can look some more at the other examples. You can also look at examples online on my YouTube channel, but you guys are free to go. Make sure you already chatted me your first and last names in case you forgot that. Also, if you're from a different class than NO2B, make sure you chat me your first and last name with the O01B or the word asynchronous or something with it. But you're free to go, and I'll wait for the last person to leave before I leave. But have a good night. Thank you for coming. Remember, we have no class on Monday. No class on Monday. Memorial Day. Oh, that's right. You guys meet on Tuesdays and Thursdays. I don't know why I told you that. Well, you still don't meet your Monday classes on Monday, at least. Anybody have any questions? You can stick around to ask. Of course, if you got to go to lab, you got to go to lab. That's cool too. But like I said, I'm just going to wait here for the last person to leave.
I was a little bit confused on the density of pure water.
Uh-huh.
I wasn't sure if I think I kind of blanked out on this section, but I understand canceling out, I think 1,000 kilograms over 1,000 meters cubed
Uh-huh.
with the 1 meter over 100 centimeters because it's cubed. So we need to kind of
Right.
multiply it 3 times. Okay. So, right. First we canceled out the kilograms
Hmm.
and then the centimeters, which got us
Grams.
1 gram over centimeters cubed. Okay. So yeah, A makes sense, I think.
Did you see that the 100 times 100 times 100 is a million? That's what a lot of people miss.
Wait, is this A? Yes. Yeah, I don't think I wrote that one down.
Oh, by the way, these are actually on my Google Docs too, so you can always go back and download my notes if you wish. They're in PDF format and they'll be on my Google Docs in the 241 Google Docs.
Okay, thank you.
Oh, and if
So
you look,
then,
it doesn't say it here, but this one's going to be called 05222025. So if you do a search for that, that'll pull the actual notes up for the specific date. That's why I use that weird naming of PHY 241 N02B 05222025, which you'll see on the video. Did you find what you were looking for there, Andrea? Andrea, whatever that would be.
Andrea, yeah.
Andrea.
But I think that one is the one like the one of the I understood A, but I don't think B and C. I
Okay.
think you said B is just sort of working off of what happened with A, right?
B is using the just below the purple sentence where it says there is an extra credit. I worked out a definition of what the liter was, and what I found was 1 liter is equal to 1,000 cubic centimeters. So
Yes.
you see that? I'll show you.
Wait, where? Okay, yes.
Okay. So if you want a milliliter, you divide this by 1,000. But if you divide that by 1,000, you have to divide this by 1,000 as well. So you end up getting 1 milliliter is equal to 1 cubic centimeter. So that's what I used right there. And that
Mm-hmm.
took my answer that I got here and made it into 1 gram per milliliter.
Oh, okay.
That makes sense?
Okay, yeah. Yeah, that does make sense. Yeah, okay. Right.
The other one was a little trickier, but to do that, I had to do this calculation. You see that, what I was saying there, Andrea? Andrea?
Yeah, I'm just trying to locate it in my notes real quick because I was um, okay, yeah, I found it. Sorry.
Okay. Anybody else have any questions while we're waiting for her?
Okay, yeah. So wait, this one is 100 kilograms over 1 meter cubed times
1,000 kilograms over 1 meter cube.
oh,
Yeah.
yeah, sorry, 1,000 kilograms. And then we multiplied it by 1 meter cubed over 1,000 liters
Hmm. And that was,
because we did the math.
yeah, we did the math over here and found that one
Hmm.
liter is 1/1000th of a cubic meter.
Okay, yeah.
Another way of saying that is 1,000 liters is a cubic meter. Or actually, a better way is a kiloliter is a cubic meter. I'm gonna write that down. I can't
What
believe
was
it.
that?
A kiloliter,
Oh,
1 kiloliter is equal to 1 cubic meter. So that's kind of nice. One
yeah.
milliliter is a cubic centimeter. 1 liter is right in between, and then 1 kiloliter is a cubic meter.
Hmm. Okay, and then this was canceled out. Okay. Okay, fantastic. I think I got it. Thank you.
Anybody else have any questions? Any questions whatsoever is completely cool, folks. Let me look at the chats real quick. I got four new ones. I want to see if anybody asked me any questions there. It looks like everybody was just chatting me your first and last name. Oh, good. I'm really excited that so many people from my asynchronous class are coming. This will definitely be a lot more helpful than people that are just wait and watch my video later. Are you in the face to face or the asynchronous class, Andrea? Or are you in this class?
Oh, I'm in this class.
Okay, cool. I think I got it. Got it.
Oh, I was actually recommended this class by another student who goes to UVA with me.
Uh-huh.
His name is Evan Smith.
Oh yeah.
You remember him? He
Yeah,
said he was the
I
one
remember
that
that
drew a
name.
bunch of potato cats, and he was like, "Oh, you should take Professor Younger's physics class."
Well, thank you. Tell them thank you very much.
Yeah, yeah. He actually just graduated this year too. So,
Awesome. Hopefully I'll hear from them pretty soon.
yeah. Thank you so much.
Welcome. Have a good one.
You too. Have a good rest of your night.
You too. Have a safe weekend, everybody. Adriel, did you have a question, sir? I did see that you sent me some text messages and messages. I've just been too busy today to reply yet. I think I got
That's it. It's Adrian.
okay.
Yeah, that's mine. The
Gotcha.
other guy, I'm not sure. Yeah, it's about the labs because I saw the lab document and I got really worried about how you're supposed to do that when you don't
Yeah.
have a lot to measure.
You might not have been here at the beginning of class, but I discovered a major problem with the lab, and that's probably given you all the fear that you're having. It
Yeah.
turns out that your instructor is kind of a moron. Okay. So what happened was I inadvertently assumed that the lab that I was teaching was linked to the N02B class, but no, the lab I'm teaching is linked to the
It's
O01.
linked to the other class, not the correct
So
one.
I just put the labs up today. I had actually put them up Tuesday and put another one up today, but then I realized it was on the wrong class. So now it's in your class. So if you look in your class in Canvas, you'll see there's a week 1 module, and then below that's another week
Yeah, the second
module
module is
lab.
the addendums, which
Yep,
is how you do the yeah, I think it's this. Oh no, the video introduction is what we need. Yeah.
exactly. That's the part where I just tell you how the lab is run, tell you how you're going to use whatever you got to use. You can still email me or text me or chat.
Okay, yeah. Even though the document is basically the same.
Exactly. The addendum is what makes it so that you can do it at home. But the main document is what you're actually filling out. Your ideal goal here is you're gonna take the Word document that represents the lab write-up, not the addendum, the other part. And everywhere you enter data with with the actual keyboard, you're gonna make sure that font is not black. Make sure it's like light blue, medium blue,
Anything but black.
anything
And
but
then
yeah, and
and then and
some of
then
them
yeah,
hard on the
the
eyes.
lab and everything we need to know is in that video
Yes. Yeah.
on how to do. Okay. Yeah, because yeah, it screwed me over, especially with the second lab, which seemed doable even without Excel. I think Google, yeah, I saw Google spreadsheets can.
Yeah. And the other thing is, I told everybody that because I screwed that up, normally the Tuesday lab would be due by 11:59 p.m. this coming Tuesday, and the lab for today would be done due by 11:59 p.m. a week from today. But if y'all need more time, just let me know. I'll give you at least until Sunday of next weekend. Just
Okay.
because I screwed up. But I don't think you'll have any problem fitting it in anyways with these two labs. But if you do, just let me know. I'm not going to be taking off any points for it being late because that's my screw up.
Yeah. Yeah. So I was also about to ask about the conceptual and the homework. Both are because both are apparently due next week, but that's the way policy thing.
Exactly. So yeah,
Yeah, I
you'll
completely
normally
forgot
have
about that.
per chapter, you'll have at least two homework sets. One will
Two
be
homeworks and two labs every week.
Yeah, at least. Sometimes there's two problem sets, but I try to stagger them. Like if you have two problem sets for a chapter, I'll make the first problem set due on for you guys it'd be Monday at 11:59, but the second one will be due on Wednesday at 11:59. So I try to do that for you.
Okay. The last one is basically about the rapid estimation because that was the one that gave me so much trouble.
Mhm. That's very much the normal one to give you trouble. That's the one that gives everybody trouble.
Yeah, because I did the practice test. The one related to it was an extremely vague. How many pennies can you fit in a 1 by 1 by 1 box?
Yep.
They give you no numbers.
But yeah, let me give you an idea of what you got to think about
That's
there.
work.
What they're expecting of you is one, you have to have some sense of how big a penny is. That means you should understand how big a centimeter is, how big a penny is, and how they're related. Not only the
Yeah,
diameter, but also the thickness.
yeah. That's going to be pretty much the whole course.
Yeah. So I would venture that, and I gave you some hints in this lab today. I mean, in this lecture today. Uh, Maybe you don't know that a centimeter, that a penny's diameter is slightly bigger than a centimeter, but I bet you know it's smaller than 2 centimeters, and I bet
I had to look. I had to look it up for mine. It said 3/4 of an inch.
yeah,
So
there you go.
yeah, that's how if that was.
Yeah, well, you won't be able to do that on a test. So
Yeah.
that's why you've got to figure out on just from everyday life, you should be able to look at things and start thinking about them in terms of how many centimeters wide is that or how many meters wide is that. Just start getting used to that because that part's going to be critical. You should be able, like I said in here, to look at the binding of a book and estimate the thickness of the pages, the total thickness of all the pages combined. And then if I told you the number of pages in that book, then you should be able to figure out how thick a single page is. But again, that requires you to understand exactly how big a centimeter is.
Exactly how big a centimeter is and how big
Yep. How
the
about,
yeah,
did you ever
it's
play with
background
Rubik's Cube?
knowledge that
Did you ever do the Rubik's Cube?
I straight up never saw Rubik's Cube. That's how dumb I am. I straight up feared physics.
Well, the reason why I was saying
And
is if you think of things that you've had a lot of experience with, like a lot of times I run into students that played with Rubik's cubes a lot while they're in high school, and I would tell them that a Rubik's cube individual square is about 1.5 centimeters wide, and now they can start seeing things in terms of how big a single square sticker is on a Rubik's cube, stuff like that, or staples, or your fingernails. You can use those as well. Doorknobs are a meter high, that sort of thing. But
mm,
that's mostly what the rapid estimation is about. And
yeah.
there's a very limited number of questions in the bank. And I showed you another one today that's not in the bank, but it's a possibility for being on the test is, hey, how many fruit flies or how many Fruit Loops fits in a shower stall? So you can do stuff like that as well, but you'd have to be able to picture in your mind how big a Fruit Loop is or how big a fruit fly is or whatever.
So if you just straight up get it wrong, then you just straight up get the estimation wrong, you get the question wrong.
Exactly.
Oh,
But
that's the kind of thing I feared.
yeah, but the good news
Uh
is it's like the answers aren't like 1.5 times 10 to the third or 1.9 times 10 to the third.
yeah,
The answer
if
is
you
like
get it like
1.5.
2 centimeters.
Yeah.
If you assume a fruit lies 2 centimeters, then you're just gonna get it wrong.
Yeah.
Boy. Uh, yeah, because yeah, this is gonna be rough for me. I am a cross. I'm a weird case. I'm a cross registration, even though I have been here at TCC before.
Uh,
I basically came back from Virginia Wesleyan
gotcha.
because I've heard some bits about the physics over there.
Mhm.
And I heard not good things. Like fall of 2024, I was told that more than half of the students in a physics class had failed, and the ones that did pass were only like relatively passing, like a C.
Oh, yeah.
So I did not like the rumors, so I came back to TCC. So
We get a few students from Virginia Wesleyan. I've got students from Virginia Commonwealth. I've got Virginia Tech, UVA, uh,
yeah,
Liberty, various other colleges. So yeah, it's pretty normal. JMU, I get a lot from JMU. I get some from North Carolina colleges on occasion too. But yeah, that we pride ourselves on being only interested in teaching the students to be as awesome as they can be. So
Okay.
I'll do
Yeah.
my
I'll
best.
have to start thinking about measurements of random things.
Well,
I've also got one more.
go ahead.
So you're at the density of water sheet.
Right.
At the very bottom, I got a little confused about the so it's 1,000 kilograms per cubic meter equals 1 kilogram per liter.
Mhm.
See, am I missing something here? Am I missing something about the liter? 1 kilometer?
You're probably missing the forest for the trees sort of scenario. It turns out that you sort of think of a centimeter and a meter pretty reasonably as differing by a factor of 100, but our brains normally don't process it too well when we're talking about cubic centimeters and cubic meters. That the cubic meter is literally a million times larger than the cubic centimeter. Because of that, you get weird little things like 1 kilogram per liter, but also 1 gram per milliliter, but also 1,000 kilograms per cubic meter. So that's sort of why it looks like the math shouldn't work out. And the only way you can make yourself feel better about it is by doing this calculation.
Because you're cubing it 3 times to get the liter.
Exactly, because you have to do the conversion factor times basically
Times
three
three.
times.
Yeah, you cube it 3 times. You do it 3 times because it's cubed. Yeah.
So 100 cubed is a million. That's why.
And that, yeah, it's basically 1 milliliter. Okay. Yeah, I think that's it for me. I'll see if I can try to get my assignments done.
No problem. Make sure you, like I said, I gave my students my cell phone number. If you try to text or email me and you don't get a response within one school day, then make sure you go ahead and follow up by texting me, or you can just text me from the get-go. It's fine either way. I've set it up that way.
Yeah, you school day is Friday. Last school day is Friday.
Yeah, Friday and
So
then Monday would be the next one.
okay, got you. Yeah. Friday had been cut off at one point, but
But
not anymore.
in this case, it excludes Monday because Monday's a Memorial Day.
Yeah, Monday. Yeah, Monday is. Yeah. Yeah, that's all. Thank you.
No
Thank you.
problem. How about you, Adriel? Do you have a question, sir? You might not be there. You there, Adriel? I guess not. All right, folks. Well, I'm going to go ahead and say bye-bye. Thanks again for coming. Thank you and bye-bye. Don't forget, you can find these notes on my Google Docs. If you find them on the internet and you want them, just email me, and I will do what I can to get them to you. Or you can just post a message in my YouTube channel, and I'll try to get back with you and send you a link so that you can access the individual notes. So have a good day. Bye-bye.